Okay, so we've gone over the bell ringer, refreshing our memory on the percent problems that we have. Today, what we want to look at is the next lesson where we are going to actually define polynomials, start to understand what a polynomial is, so then when they start mentioning polynomial, you understand the terminology. We're going to look at graphing linear equations. We want to understand what gives us a linear equation and what that graph actually looks like. There's a method that you can use in order to do that, but then we can look at a simpler method known as the intercept slope method of graphing. So there's two different ways we're going to look at graphing those linear equations. And linear equations are from polynomials, so that's why we need to talk about polynomials first. So that's what we want to focus on today. So the first thing that they talk about, we want to get to an understanding of what a polynomial is. So keep it basic, keep it simple to begin with. Let's just look at what a simple expression is. I have some simple expressions listed. We have -4. That's a pretty simple expression. We have 1/2. You can talk about 2x as a simple expression. -3x squared is a simple expression. This is still pretty simple. -5x squared plus 6x plus 2. The only reason it's a little more complicated than the first 4 that I have listed is because it actually has 3 terms. So we've gotten into more terms, but it still is a simple expression. What is a simple expression? It says that you have real number coefficients. Real number coefficients. If I look at real number coefficients, let's get rid of that purple because it's going to clash. So if I talk about real number coefficients as far as simple expressions are concerned, what's a real number? Give me an example of a real number. 1. What's another one? -4. What's another one? (32.5). What about the square root of 17? Is that a real number? The square root of 17 is an irrational number, and are irrational numbers reals? Yes. So the square root of 17. Right now, everything you've worked with is a real number. The only thing that's not a real number is an imaginary number, and an imaginary number is a square root of a negative number. So as long as I don't have that, I have a real number. So if I look at it, each one of these coefficients, everything I have highlighted there, those are real number coefficients. So they're leading us into what is known as a simple expression. The other thing that we have to have when we deal with simple expressions is variables with whole number exponents. What's a whole number? 0, 1, 2, 3, 4, 5. So if I look at the exponents, right here I have an exponent. What's that understood to be? x2, if I just say x, it's understood to be to the first power. Is 1 a whole number? Yes. I look at the next example and my exponent is 2. If I look at this trinomial, I have exponents of 2, 1. And then what happens over here when I talk about just these whole numbers? Do they actually have, or I should not whole numbers, but when I talk about these real numbers, just as a constant, do they actually have whole number exponents? Well, this is the -4 is the same thing as -4x to the 0 power. Is 0 a whole number? Yes, you just told me that. Jada said, oh, whole numbers are 0, 1, 2, 3. So this still has a whole number exponent. It's just that what is x to the 0 power? 1, and it simplifies into -4, or what we see is -4. So 1/2. 1/2 means the same thing as 1/2 x to the 0 power. So the exponent of that variable, which is the 0, is still a whole number, and that's why we consider just 1/2 or -4 to be simple expressions. The x, as we mentioned, is understood to be the first. We come back over here into the trinomial. and you have plus 6x to the first plus 2. This is x to the 0. So the yellow tells us that we have real number coefficients. The blue tells you that the variables have exponents that are whole numbers, and they are. They're not negative numbers, which is integers. They're not fractions, which is rational numbers. They're not a decimal that can be written as a fraction, which is your rational numbers again. They are whole numbers. When I start talking about each one of these examples up here that I have underlined in purple, they come up with a name to refer to all of them instead of just saying simple expressions. Your book mentions, oh, wouldn't it be nice if they could just call it Binomials because they're simple. But instead they give you this complicated word that says polynomials. And the only thing that polynomials are, poly kind of means, what does poly mean as a prefix? Many. So it means many terms, but those terms have to be simple. So you have to have real number coefficients, and whole number exponents. And as long as you have that, you have what's considered a polynomial. Polynomial. It sounds complicated, but they tell you it's simple. Just look for real number coefficients and whole number exponents. Can I change the slide? So when we talk about these polynomials, now I'm going to go back to this slide. I had 1, 2, 3, 4, 5 examples up there. You notice the first 2 are probably the simplest, but the first 4 had something in common based off of the last one. And it was that they are single terms. There's only one term. So we have another word that we can use, and it's something called a monomial. A monomial is just when you have a polynomial in one variable. That means that I'm not having 5xy. So one variable, I just want one variable, not something like 5xy where I have 2 variables. Okay. So one variable with one term. That's it. -4, one variable. Yeah, actually it's x to the 0, remember. One variable and one term. 3, x to the 1 or to the 14. One variable, one term. 4 thousandths, x to the 5th. One variable, one term. Radical 2, x, one variable, one term. Keep in mind, the square root of 2, square root of 2 is a real number. That's why I asked you about the square root of 17 earlier. We come over here and you have 2x squared. One variable, which is x, one term. There's no plus or minuses after that, grouping it together. So we refer to it as a monomial. Mono meaning one, singular. No big deal. Can I change the slide? So we look at the next thing that can happen. What happens if you have 2 terms? Well, it's considered a binomial. We have x plus 2 is an example. I have 2 terms. Binomial. You have x to the 4th plus 2x. Binomial. 2 terms. 1, 2. 1, 2. 2 terms. If you get 3 terms, such as that very first example I gave you, I think we had 3 terms, you get into something called a trinomial because you have 1, 2, 3 terms. But each one of those terms will have a real number coefficient and a whole number exponent of your variable. Now later on we're going to get into some factoring of some polynomials. There's special things you can do when you multiply binomials together. A special way to factor a binomial. If it's a perfect square, things like that. And then when you start talking about these polynomials, there's even more important information when you start talking about the graphs of them. All right, I want to give you I'm going to give you a minute with a partner to define a polynomial, a monomial, a binomial, and a trinomial. What are you going to do? Taylor? Monomial, binomial, and trinomial along with polynomial. How long do you get? 1 minute. Go. Okay, so Jacob, what is a polynomial again? What are the two requirements to have a polynomial? Very good. Real number coefficient and a whole number exponent. Marley, what is a monomial? Yep. Polynomial is going to have one variable and it'll have one term. What's a binomial, Caleb? Polynomial with two terms. Julie, what's a trinomial? Polynomial with three terms. Very good. So the next thing that we need to discuss about these so we can understand something about the graph is the degree of the polynomial. And the degree of the polynomial is the highest degree term of the polynomial. If we are with one variable, it's just going to be which one of the x's has the highest power. It's going to be the highest power of x. So if I look at the first example that I have up here, x plus 2, first of all, what type of a polynomial is that? Very good. It's a binomial. And what degree would it be? Well, I look at the highest power of the variable. I have x to the first, and this is x to the 0. So which one's higher? The first. So this is a first degree, and it is a binomial. So if I want to get specific, I could say it's a first degree binomial. If I look at the next example, I have x to the 4th plus 2x. What type of a polynomial is it? Binomial, because I have two terms. I have x to the first. Oh, sorry, I said it, so I'll put it there. I have an x to the first and an x to the 4th. So what degree is this binomial? What's the highest power? 4. So this is a 4th degree binomial. It's a 4th degree, so you look for the highest power. If I look at the exponents for the last example, what kind of a polynomial is it? Trinomial, because I have three terms. I have a square, x squared, x to the first, and this is understood to be x to the 0. So what is the highest power? Second. So we call that a second degree trinomial. Now, something that gets a little confusing is we call those quadratics. That gets really confusing because you think of quads as being 4 sometimes. But we're going to work with these second degree a little bit later. The graph of those gives you something that is a parabola. So when I see x squared is the highest power, that's going to tell me something. That's why this is important. If it's a second degree, one, it's got to be one variable. Actually, you're going to have two if you put it into an equation. But you get a graph that looks like this, which is called a parabola. You get a U shape. It could turn down if you want to. Specific things that make it open up and open down. Just a little quick blurb about that. If the coefficient is negative, it opens down. And if that coefficient of x squared is positive, it opens up. Give you a little idea. But what we want to focus on is we want to focus on if I change this into an equation, which means I'm going to have another variable involved. Equation that contains only polynomial terms is considered to be a polynomial equation. Equals something. And if I have the degree of a polynomial equation, which is the same as the highest degree of the term in the equation, I already did that. Why did I put that down again? Just a minute. Okay. I don't know why I stated that again. The degree of the polynomial equation is the same as the degree of the highest degree term in the equation. What we want to start looking at is what happens when I get something like this. What does that mean to any of us? Probably nothing. But we're going to start giving it meaning by making it turn into a graph. And graphs tell you a lot. You look at graphs whenever you're trying to find values of specific information. Science, you can graph a lot, so you can predict into the future. History, social studies, you might find graphs using predictions for populations, information like that. So we want to be able to look at those. If I look at the following equations that I have listed there for you, they are all polynomial equations. I have an x and a y and an equal, so they're not a single variable, but it's still considered a polynomial. What do you notice about the degree of each one of those? I know why I had that stated before, because I actually said the degree of an equation instead of an expression. The degree of the equation is still going to be the same. If I look at this, both of these are to the first power. So it's a first degree equation. The next one, both variables are raised to the first power. It's a first degree equation. The next one is a first degree equation because both variables x and y are to the first power. And that leads us into the graph of the first degree polynomial equation. If I have two unknowns, the graph of that is going to be a straight line. So we're going to work on graphing these polynomial equations, and there's two different methods that we are going to use. If I come back to this, this gives you a line, believe it or not. Some algebraic equation that you see is going to give you a line. And the same thing for the last one, negative 3x is equal to 2y plus 4. There's different formats, there are arrangements of them. I have x and y on the same side of the equation. I have x by itself. I could put y on the side of the equation by itself. We want to be able to manipulate those and rearrange them so we can graph those lines.